Okay, step number 3. Determine the total number of PV modules. So the following design steps are applicable for string and central inverters only. Based on the input from step 1, you need to determine the total possible number of PV modules to be installed. The possible scenarios are as follows. Scenario number 1, architecture constraint or area constraint. Scenario number 2, budget constraint, and scenario number 3 is energy constraint. Scenario number 1, architecture constraint. So in this case, the roof area is the main constraint. You need to measure the length of the roof and the width of the roof of the PV space area. Assume the gap G between PV module is X meter. For example, in Malaysia, the gap is about 10 to 20 millimeter. The length of the module is Lm and the width of the module is Wm. Consider lengthwise up module. So this lengthwise up is actually we call lengthwise up is a portrait orientation. Okay, example here. So this is a rooftop. Sorry, my drawings is not really good. Example here, you want to put a PV module here. This is lengthwise up or portrait orientation. So here is the width of the rooftop. W roof. And here is the length of the rooftop. L roof. So this is the length of the module, and then this is the width of the module. So this is Lm, and this side is the Wm. Okay. So to calculate number of module that's suitable for this area, we start with N across up. Across up means across the length of the rooftop, and the orientation is lengthwise up. So you round down. This is the length of the roof. Divide with the width of the module plus X. X is this area. Between these two modules, we have gap here. So this is X. Okay. So then you will get the value for this arrangement. Okay. Okay. Next one is N up. Up means the arrangement of the PV module going up, and another up here is lengthwise up. So you need to round down. Width of the roof divide with the length of the module plus gap. So this is the gap area. So N total up equals to N across up multiply with N up. So N up is this direction. Okay. So why we round down? This is because if we round up, it's already exceed this area. So if we round down, we don't exceed this space. Okay, the number of module is not exceed to this space. Okay, another orientation is consider lengthwise across. Lengthwise across is the landscape orientation. So same concept. So you have a rooftop here. So this is the landscape orientation or lengthwise across. So this is an across. Okay. Another one is an up across. Okay. So an across, this across represent the lengthwise across, and the arrangement is across the length of the rooftop. Okay. So this is the length of the rooftop, and this is the length of the module, and this is the width of the module, and here is the width of the rooftop. So n across this direction, round down length of the roof divide with length of the PV module plus gap. Okay, x. This is x. N up across going up for lengthwise across. So round down the width of the roof divide with the width of the module plus gap here. So n total across equals to n across multiply with n up across. So finally, for actual installation, choose the highest value between equation 1 and 2. If both values are similar, then lengthwise across is preferred due to less effect of the accumulative dirt on the PV module. Okay, let's see example number 1. Given PV space area, the width of the roof 10 meter and the length of the roof is 5 meter. Type of PV module to be installed, Yinli Panda YL265C-30B. What is the maximum number of PV module that can fit on the given PV space area? Assume the gap between module is 20 mm. So this is the X. So you need to calculate for both orientation, lengthwise up and lengthwise across. So the length of the module, you need to refer to the datasheet of the PV module. So let's see the datasheet. Okay. So for this one, you can refer to this diagram. Okay, you must include the frame. So this is the width of the module, 990 mm. And here is the length of the module, 1650 mm. Or you can refer here in the dimensions, length, width, and height. Okay, so 1650 mm or 990 mm or 40 mm thickness. So this is the length, and this is the width, and this is the thickness of the PV module. Okay, and then you calculate for both orientation, and so the maximum number is 20 module, which lengthwise up arrangement. So you take the maximum number. Okay, why you take the maximum number? The more the biggest number of the PV module, it will produce more power. Scenario number 2, budget constraint. In this case, the owner has a limited budget allocated for this project. You need to find out the latest GCPV system cost index. The total affordable number of PV module is calculated using N total estimated equals to round down, budget allocated in Ringgit Malaysia, GCPV system cost index in Ringgit Malaysia per watt peak, and multiply with BMP STC of the PV module. So the present 2016 GCPV cost index is about 8 ringgit per watt peak. The owner has allocated 40,000 ringgit Malaysia in the GCPV project. How many Yinli YL265C-30B PV module can be purchased? So from the information, we know that the present cost index is RM 8 ringgit per watt peak, budget 40,000, and from the datasheet of the PV module, you get 265 watt peak. So let's check. So this is the model 265. Okay, this is the power output. So this is the PMP STC of this PV module, which is 265 watt. So you calculate the total affordable PV array module is 18 modules. So you need to round down to 18. So if you run up, it will be more than the budget. That's why you need to round down. Okay, scenario number 3 is the energy constraint. In this case, the owner requires certain percentage, X percentage, of his or her total annual energy consumption come from the GCPV system. You could determine the total number of PV module required by N total estimate equals to how many percentage of the total annual energy consumption in watt hour divide with PMP/STC multiply with peak sun hour multiply with mismatch factor multiply with dirt factor, temperature factor, cable loss, efficiency of the inverter, and the aging factor. So how many losses? 1, 2, 3, 4, 5, 6. 6 losses. Okay. Multiply with peak sun hour. So this is peak sun hour. The unit in hours. Multiply with PMP STC. So PMP STC, this is a data sheet, come from the data sheet of the PV module. This peak sun hour you can get from the nearest metallurgical department. Okay. Or you get the data from the software, for example, PV6. You will know the peak sun hour for that location. So power multiply with hour, you will get in energy. So this is energy consumption and this is the energy from the PV system. Okay. Now from the above scenario, choose the lowest number as the actual total number of PV module to be used in the design. So let's see this example. The monthly energy consumption of your customer is shown below. So example here, you get this data from the electricity bill from January to December. So this is the total amount of energy, 6,176 kilowatt hour. Assuming the following factor, so this is the peak sun hour annually, 1715.5 hours. K-dirt, we using Malaysia standard, which is maximum losses 3%. So 3% equals to 0.97. Average maximum ambient temperature, this is ambient temperature under Malaysia climate, 35 degrees Celsius. K cable, this is a voltage drop or cable loss, 0.97. Efficiency of the inverter, this one you can get from the data sheet of the inverter, 0.97. And this is a new PV module. So for the new PV module, you can assume KH equals to 100%. Okay, aging, aging 100%, which is KH equals to 1. For new PV module also, you can assume this K dirt equals to 1, which is no dirt. But in this example, we assume K dirt for the worst condition, 0.97. So how many PV module required to achieve at least 90% of the total annual energy consumption supplied by the GCPV system? Okay, solution for example 3. The target percentage more than 90%. Total annual energy consumption is 6,176 kilowatt hour. PMP/STC 265 watt peak, peak sun hour 1715.5 hour, mismatch factor 1, K-dirt 0.97, ambient temperature 35 degrees C, K-temp you need to calculate temperature factor. So this temperature factor you calculate for power. Okay, temperature factor for power 1 plus gamma, percentage gamma BMP over 100 multiply with Tm minus TSTC. So Tm minus TSTC is equals to T ambient, T average ambient. So you will get K temp equals to 0.8425. Okay. So this is percentage gamma BMP from the datasheet of Yingli Panda. So the total estimated energy is 15 module. You need to round up. So it will be 16. So why you round up? Because the target is 90%, more than 90%. If you round down, you won't get this 90% and above. So should use 60 unit of PV module or more to achieve the target percentage. Example 4, for example 1, 2, 3, how many PV module we use in your design? So we need to summarize for example number 1, which is based on area, you get 20 modules. But for example 2, based on the budget, you only can buy 18 modules. But for example number 3, which is the target percentage, more than 90%, you get not less than 60 module. So from this example here, for all the constraint, you need to include all example here. So you should choose 18 modules because you cannot choose 20 because it's already surpassed the budget. Okay, because your budget only for 18 modules. And you cannot choose less than 16 module. If you choose less than 16 module, you cannot get the target percentage, which is 90% and above. Okay, step number 4, sizing PV array with inverter. The size of inverter required that match with the PV array is determined using N total estimate multiply with BMPs DC multiply with 0.9. This is safety factor 0.9 to 1. So N total multiply with BMPs DC multiply with 1. So this is power from the PV module, from the PV array, 0.9% to 100%. So from this range, you need to find the suitable inverter. Okay, P nominal inverter required. Now, you choose any inverter that satisfies with the above requirement. Example number 5, the total number of Yingli YL265-30B required is 18 modules. Suggest a suitable inverter. So, N total estimate 18. So, PMP STC from the datasheet 265 watt. So, you calculate the value. So, the P nominal inverter required is between 4293 watt and 4770 watt. So in this range, let's take Sunny Boy 5000 TL. Note there are two versions of SB 5000 TL. One with adjustable and displacement power factor, and the other one is without adjustable and displacement power factor. So choose the one without adjustment and disable power factor with nominal power 4600 watt, which satisfy the above condition. Okay, let's see this datasheet of the inverter. Okay, so we refer to this datasheet of the inverter, Sunny Boy 5000 TL. So the P nominal inverter required is actually on the AC side, which is rated power 4600 watt. So this is the value of the P nominal of the inverter. So from the student inverter, you could determine the range of the total number of PV module that match with the inverter. So now you already know the P nominal inverter, which is 4600. Now you calculate again the total number of PV module that's suitable for the inverter. So P nominal inverter 4600, BMP STC of the PV module from the datasheet is 265 watt. Calculate, you get N total between 18 to 19. So based on example 1 to 5, so the optimum number is 18 PV modules. Okay, because of the constraint we consider the constraint for example 1 until example number 5. So determine the minimum number of PV module in series per string. So NS minimum equals to round up V minimum window inverter multiply with 1.1 over V min MP multiply with kV drop. So this is the minimum voltage of the MPPT window multiply with 1.1. Why we multiply with 1.1? This is because we consider the cell temperature. From this equation, V min MP, to calculate the V min MP, equals to VMP STC multiply with temperature factor. 1 plus percentage gamma VNP over 100, because this is in the percentage, multiply with T cell minus 25 degrees Celsius. This is temperature at TSTC. So while voltage will be minimum at maximum cell temperature, remember back the characteristic of the PV module. When the temperature increase, the voltage will slightly drop. Okay? When the voltage is slightly drop, you don't want your inverter turn off during solar noon. That's why you need to multiply with 1.1. If you don't multiply with 1.1 during solar noon, your inverter will turn off. Okay? So that's why we multiply with 1.1 to avoid that happen. So example 7, determine the minimum number of Yingli YL265C-30B PV module in series so that during the highest cell temperature, the inverter still working in MPPT mode. So VMP STC, this is from the data sheet of the Yingli Panda. Percentage gamma VNP minus 0.45. Okay. If not given, then use percentage gamma VNP. So let's refer to the data sheet of this module. Let's check. So percentage of gamma VNP. Okay, percentage of gamma PNP is minus 0.42. So we have a mistake here. So we assume that the percentage of gamma VNP. Oh, this is gamma VNP. Let's check gamma VNP. Gamma VNP. Okay, this is for gamma VNP. Temperature coefficient for VNPP. So minus 0.41. Okay, so there will be mistake here. So let's say we assume the gamma VNP equals to minus 0.45. So the maximum cell temperature under Malaysia climate is 75 degrees Celsius. So we calculate V min. This is from the data sheet. V min window inverter 175. So that one you need to refer to the data sheet of the inverter. So refer to the MPP voltage range. So the minimum one is 175 under MPPT mode, and without MPPT mode, the lowest one is 125 volt. So for this minimum window inverter min under MPPT mode, so the value is 175 volt. So voltage drop, we assume worst case, which is 3% losses, 0.97. So calculate V min MP. So V min MP by using this equation, BMP STC multiply with temperature factor. So you get 24.025 volt. And then from this you calculate NS minimum by using this equation. So 8.2603, you need to round up to 9. So why the NS minimum we round up to 9? This is because this equation is already the minimum number. If we round down, it will be less than minimum. Okay. So determine the maximum number of PV module in series per string using NS max equals to round down V max inverter. So this is the maximum input voltage of the inverter. Multiply with 0.95. This is safety factor. Divide with maximum voltage during open circuit. So here is the equation of Vmax OC equals to VOC STC multiplied with temperature factor during open circuit voltage. So 1 plus percentage gamma VOC divided with 100 because of the percentage. Multiply with T cell minimum minus 25 degrees Celsius. This is T STC. Why we use this T cell minimum? Please remember the graph, the characteristic of PV module. At low temperature, the voltage will be high. Okay, that's why when we calculate Vmax during open circuit, we consider this minimum cell temperature. So Vmax inverter multiply with 0.95. This is safety factor. Okay, because at the low temperature, the voltage will be increased. So the voltage will be high. That's why we multiply with 0.95 as a safety factor. For example here, in one condition, so it's a rainy day. So after the rain stop, the sun is appear. Of course, there is a value for the solar irradiance. But the module temperature is still low. Okay. If the module temperature is still low, so the voltage will be high. That's why you multiply with 0.95. This is as a safety factor. Example number 8. Determine the maximum number of Yingli YL265C-30B PV module in series so that during the lowest cell temperature, the inverter will not damage due to over voltage. So VOC STC 39 volt. This is from the datasheet of the PV module. Percentage gamma VOC minus 0.31%. So let's check, is it correct? So let's check. So 265 percentage of the gamma VOC minus 0.31 is correct. and then the value for VOC STC, which is 39 volt. Okay. Okay, so this is correct. TCL minimum under Malaysia climate, which is 20 degree Celsius. So Vmax inverter equals to 550 volt. This one you can get from the datasheet of the inverter. So maximum DC voltage, please remember this is on the DC side of the inverter, which is connected to the PV array. So 550 volt. Okay, so this is the maximum DC voltage. So Vmax inverter 550 volt. So calculate NS max. So before you calculate NS max, first calculate Vmax OC. So you get Vmax OC 39.6 volt. And then calculate NS max, you get 13.19. And then you need to round down. This is because this is already maximum. If you round up, you get more than maximum. So after you calculate NS minimum, so number of PV module in series per string for minimum and maximum. The next step is to calculate the maximum parallel string using NP round down IDC max inverter divide with ISC STC of the PV module multiply with 1.25. Okay, remember that when we make a parallel connection of the PV module, of course the current will increase. So we must consider the current from the PV array and the current from the inverter. So this is inverter and this is from the PV array. So determine the maximum number of Yingli YL26530B PV string that could be connected to the SB5000TL inverter. Solution. Okay, in this inverter, we have input A and input B. So let's refer to this. Okay, so this is input A and this is input B. Why we have input A and input B? This is because this inverter have two MPPT tracker. Multiple MPPT, number of MPPT tracker. 2. For each MPPT, you have 2 string for MPPT A and 2 string for MPPT B. So that's why you have input A and input B. 15 ampere, 50 ampere is the input of in input DC max of the inverter. So where is 15 ampere? You refer to this. So maximum input current 2 multiplied with 15 because you have 2 MPPT. So for each MPPT, the input is 15 ampere. So 50 ampere to 50 ampere, IST STC is 8.93. This is the data from the datasheet of the PV module. So refer the datasheet of PV module. So IMP STC, this is 8.93 here. So NPmax calculate by using this equation, you get for NPmax for MPPT-A, you round down 1, and MPPT-max for MPPT-B, so 1 maximum parallel string. You need to round down because this is already maximum. Okay. So as in summary, you have N total, NS minimum, NS maximum, and the value of NP max. So thus you could determine the optimum PV array configuration NP by NS that need to satisfy all the above conditions. So let's see example 10. Determine the optimum Yingli YL265C-30B PV array configuration that match with Sunny Boy 4000 TL inverter. So this is actually 5000 TL inverter. Okay, so please make correction here. So the solution from example number 4, we get 18 modules required that satisfy with the space, budget and the energy requirement. And then from example 6, which is based on the inverter, we get the range of PV module between 18 to 19 modules. For example 7 and 8, we get NS minimum 9 and NS maximum 13 module in series per string. And for example number 9, we calculate the maximum parallel string and PMAX, which is 2. 2 means one for MPPT A, another one from the MPPT B. So the optimal PV array configuration should be 2 by 9. Okay, why 2 by 9? So 2 by 9 equals to 18. So it's satisfied with this one. And total, the range of the PV module from the inverter size. And 9 is a number of PV modules in series per string, which is within this range, 9 to 13. And maximum number of PV module is 2. Okay, so 2 by 9 equals to 18. Let's say you put 3 by 9, so you already get 27. So 27 module is not satisfied for all this condition. What about 1 by 13? Okay, 1 by 13. So it satisfy this one within the range. Satisfied with this one because this is maximum. Maximum is 2. You can use 1 also because the maximum is 2. But if you put 1 by 13, satisfy this one, satisfy this one. But 2 multiplied with 13, you get total 26. So it's not within this range and also exceed the maximum number of the PV module. Okay, so this one you need to try and error until the PV array configuration satisfy all these conditions. Step number 5, design the balance of system components. So this we need to calculate the voltage and current rating of the following component. Example here, DC fuse. This is the equation from the Malaysia standard I trip for DC fuse. 1.5 multiply with ISC STC of the PV module and 2 multiply with ISC STC of the PV module. So the voltage is rating is commonly 1000 volt DC. So example 11, determine the tripping current of string fuse based on the PV array configuration in example 10. So PV array configuration on example 10 is 2 by 9. Okay. So 1.5 multiply with ISC STC, which is 8.93, and 2 multiply with 8.93, so you get 17.86. So the I trip is between 13.395 to 17.86. So this is the tripping current for the string fuse. So DC SPD, DC breaker. Okay, this is the rating of the breaker. VDC rating greater than 1.2 multiply with VOC STC multiply with number of PV module in series per string. Okay, because when you series the PV module, of course the voltage will increase. So this rating will cover the whole PV modules in series per string. IDC rating, which is cover all the parallel string, must be greater than 1.3 multiplied with ISC STC. Don't forget, this is the number of parallel string. Let's see example 12. Determine the minimum voltage and current rating of DC main switch. So VOC STC and ISC STC you can get from the datasheet of the PV module. This is the optimum PV configuration from the previous example 2/9. So VDC rating and IDC rating by using this equation, we get 4 to 1.2, 23.218 ampere. So you can buy the DC main switch that greater than this value. AC breaker and bypass diode. So V diode bypass equals to 2 times VOC module STC. This is bypass diode below the PV module. Okay. This is not blocking diode. This is bypass diode below the is in the junction board of the PV module. So I diode bypass equals to or greater than or equals to 1.3 multiplied with IAC STC of the PV module. Let's see this example. If bypass diode in example 10 is faulty, what should be the voltage and current rating of the new bypass diode? So this is the value from the datasheet to calculate the bypass diode by using this equation. So diode bypass 78 volt and I diode is equals to 11.609 ampere. So you can buy the bypass diode that satisfies this equation, which is greater or equal to this value. Okay, size of the following component. This is for DC cable. So A string cable square millimeter equals to 2 times of the length of the cable in meter multiplied with IMP STC unit in ampere, and rho is the resistivity of the wire. So if the wire is copper, the resistivity is 1/56, and if the wire is aluminium, the resistivity will be 1/34. So divide with percentage of the voltage drop. So percentage we draw over 100 to eliminate this percentage. Multiply with BMP unit in volt. So this BMP you already learned in the previous example, which is example number 7. Multiply with number of PV module in series. Why we multiply with NS? Because this is the string cable, the size of the string cable. Here we multiply with 2 because we take a summarization that for positive root of the terminal and the negative row of the terminals, so we have 2 length of the cable, positive, negative. That's why you multiply with 2. So length multiply with current multiply with resistivity. So this is you get the voltage. So this is also voltage. Okay, you divide this, you get square millimeter. So this is the size of the array cable. Okay, the current carrying capacity of the string cable CCC. So this CCC of the cable should be greater than 2 times of IAC STC. The unit is ampere. Okay, for array cable square millimeter, same equation like this one, but please remember this is array. So this is size of array cable, which is already combined with the number of parallel string. So this one you need the NP. Okay, multiply with number of parallel string. So this is the length of the array cable, not the string cable. So other than that, still the same characteristic. So the current carrying capacity CCC of array cable should be greater than or equal 1.3 multiply with number of parallel string multiply with IAC STC. So the unit in ampere. So let's go through example 14. So the length of the string and array cable in example 10 are as follow. Okay, we have string number 1. This is positive string cable. We measure, we get 10 meter. Negative string cable, 15 meter. And then another string for string number 2, positive string cable about 15.5 meter. Negative string cable is about 20.5 millimeter. So where is all this string cable? So this string cable is actually the connection between the PV modules. If you refer to the schematic diagram, so here is the string cable. Okay. So the string cable usually connected in parallel. That means you connect all with number of parallel string in the array junction box. So usually all of this inside the array junction box. So this is the string cable, and here is the array cable. So array cable is shorter than string cable. Okay. So determine the minimum size of string and array cable if the maximum allowable voltage drop in string cable is 1% and 2% in array cable. If the standard DC cable available are 2.5 millimeter, square millimeter, 4 square millimeter, 6 square millimeter, and 8 square millimeter. So this is the choice, standard size of the DC cable. So what should be the actual size of string and array cable? So first you consider the longest string cable. Okay, if you refer to string 1 and string 2, the longest one is the negative string cable, which is 20.5 meters. So you take the longest one and then you calculate. So this is the copper wire. So the raw is 1 over 56. So you get 0.017857. So the percentage voltage drop in the design, you assume that the voltage drop is 1% for string cable. So 1%, 1 over 100, so you get 0.01. Vmin and P, this is, you already learned this in example number 7, which is when you calculate an S-min, you need to find the Vmin first. Okay, this is the value of the number of PV module in series that we already calculate in the previous example, which is 9. So from this equation, A string cable, so you will get 2.895 square millimeter. So this 2.89 square millimeter, so you have this choice 2.5, 4, 6 and 8. So the most suitable is 4 square millimeter.